Okay, on to section 51 and an extension of Cauchy's integral formula. Okay, we left off relating the value of an analytic function with the value of a certain type of integral. In this section, we're going to do something similar, but instead of involving the value of the function, it's going to involve values of the derivative of the function, and those will be expressed in terms of integrals as well. Specifically, the general Cauchy integral formula says let f be analytic inside and on simple closed contour C, where C is positively oriented. Okay, same hypotheses as we had in Cauchy's integral formula so far. If z sub 0 is any interior point to C, then the nth derivative of f at z sub 0 exists, and the nth derivative of f at z sub 0 equals the value of this integral. And we got an n factorial over 2 pi I integral over C, f of z, similar to what we had in Cauchy's integral formula, over z minus 0 to the n plus 1. So what's new is the n stuff. In fact, if we'll set n equal to 0, we'd have f of z over z minus z sub 0, like we did in Cauchy's integral formula. 0 factorial is 1. We'd have a 1 there. The 0th derivative is the function itself. When n equals 0, this is Cauchy's integral formula, so this is certainly a generalization. Something wild in this is something very shocking that doesn't happen in the real setting. We've assumed this function is analytic, which to us just means differentiable on open regions. And we've got, apparently, that this function's infinitely differentiable. Derivatives of all order for this function exist at point z sub 0, which is a giant step towards writing this function as a power series. We need a little bit more, but this, under an assumption simply of differentiability on open intervals, has given us infinitely differentiable. This is the first time we've seen that an analytic function is infinitely differentiable. Now, I told you to think power series representation when you hear the word analytic, and this is certainly some strong evidence that we're on the right track with that. So we have defined analytic to mean first derivative exists on open sets. And from that, we're drawing a conclusion of infinitely differentiable at points inside that open set. So can't make enough noise about that, really, that we're not going to be able to appreciate that until we get into chapter 5. In terms of proofs, when n equals 0, we had a proof. It was a pretty elementary epsilon delta proof given in the previous section. When n equals 1, there's a proof in the book that'll be given below. Maybe we'll omit that from the video. When n equals 2, there's a proof outlined in some of the exercises in the book. For general n, Brown and Churchill, they don't go there. I have notes posted. This is a standard thing to prove in a graduate level complex analysis class. So there's a link to a proof in general given in the notes. So let's just illustrate how to use this. So I'll probably be going back and forth between the general formula and these particular examples. Example 51.1. Let C be a positively oriented unit circle, mod z equals 1, f of z equals e to the 2z. Then let's evaluate this integral. Okay, we've got a nice analytic, in fact, entire function in the numerator. In the denominator, I want to take this and think of it as z minus 0 to the 3 plus 1 power. In the numerator, we've got the nice analytic function, the f of z. Now, if I look at this integral, that looks just like what we had in the general Cauchy's integral. We had, well, we don't have this coefficient here, so we have to balance the books with that, but we had f of z dz over z minus z sub 0 to the n plus 1. Our f of z is e to the 2z, and our n, because we had a denominator of 4th power, our n will be 3, and z sub 0 for what we had will be 0. We simply had a z in the denominator. Okay, so this is what we get in terms of comparing things to the general Cauchy's integral formula. We know how to evaluate this. It would be, we had n equals 3. It would be 2 pi I over n factorial, 2 pi I over 3 factorial. N was 3 times the third derivative of that function evaluated at z sub 0. Cross multiply, we'll get a 2 pi I in the numerator. We'll get an n factorial in the denominator. Nth derivative, z sub 0. We had z sub 0 is 0 in this example. So we get exactly this. We need the third derivative. Are you good at taking derivatives? Certainly. So one of the advantages is, hey, integrals aren't always easy to evaluate, but if we can relate integrals to derivatives, derivatives are easy to evaluate. And in a sense, that's what this does. So we need a third derivative of e to the 2z, differentiate it 3 times. The power rule will give you 3 multiples of 2. That'll produce an 8 out front. So we'll have 8 e to the 2z, evaluated at 0. So 8 e to the 2 times 0. And simplifying, that gives us 8 pi I over 3. So we've evaluated this integral really without integrating, but by differentiating. That's a useful thing of the general Cauchy's integral formula. Let's take a look at another one. Let z sub 0 be any interior point to a positively oriented simple closed curve C. When f of z equals 1, well, that's a constant function. It's an entire function. And n equals 0, then we have the integral over c dz, z minus e sub 0 to the 1 power equals 2 pi I. Right, we've done that before in an exercise. Also comes out of, this would just be Cauchy's integral formula. Here we're taking n equals to 0. We had the 1 there. So we get a 0 factorial somewhere in this. And function values are 1. But we can also evaluate integrals over c dz with an integrand of 1 over z minus z sub 0 to the n plus 1. Okay, this fits the general Cauchy's formula. We need the general one now because that exponent isn't just a 1 in the denominator, it's an n plus 1. So we'll have the 2 pi I over n factorial as described above. Nth derivative of f evaluated at z sub 0. Well, this is f of z equals 1. So its first derivative, and from there on out, any of its derivatives are 0. So we'll get 0 out of the derivative stuff, and we'll have an integral over c dz 1 over z minus z sub 0 to the n plus 1. That integral 0, where n is any natural number. 1, 2, 3. So that exponent is at least 2. If that exponent's 1, you know the kind of behavior we get from the previous line. When that exponent is greater than 1, you get those integrals to be 0. And we had an exercise involving that, and also some things where the exponents were negative. Of course, if I got negative exponents in the denominator, I move things to the numerator, and it's an easier story. But we've seen that before. There's how we can extract that same result from the general Cauchy's integral formula.